Welcome to the deep dive. Today, we are wrestling with a question that, well, it's defined speculative physics for decades. Honestly, it's usually just science fiction, right? We're diving into a huge challenge. Are wormholes real? And, if they are, how could any physical theory possibly show how to stabilize them?
Yeah, it's really the central gravitational puzzle of the last century, isn't it? General relativity, Einstein's theory, it allows the idea of traversable wormholes, shortcuts through spacetime. But classically, it just slams the door shut on them actually existing.
Why is that? What's the roadblock?
The problem is holding that cosmic door open. You need something called exotic matter, basically stuff with negative energy density. And classical physics, it just can't deliver that kind of repulsive force, not sustainably.
Right. That's the wall we always hit. Exotic matter isn't just hard to find. It fundamentally breaks the energy rules that classical gravity relies on. It's like saying you need, unobtainium to build your bridge. It's just not in the toolkit.
Exactly. But the core thesis we're digging into today suggests a totally different way of looking at it. Maybe the problem isn't finding exotic matter. Maybe it's that our description of the vacuum itself is incomplete. So we're introducing what we call the quantum unified vacuum theorem, or the Qμ theorem for short.
Okay, Qμ. What's the core idea there? What does this theorem actually say?
Well, it asserts that wormholes aren't just consistent with reality, mathematically speaking, but that the quantum informational structure of the vacuum itself, it automatically provides the stabilizing force needed.
Automatically?
Yes. Our core thesis is essentially this. The entanglement stress energy tensor, this Qμ, it generates the precise repulsive pressure you need to stabilize a wormhole's throat. It effectively replaces the need for hypothetical exotic matter with, well, a verifiable property of quantum spacetime itself. The entanglement is the stabilizer.
Okay, hang on. You're saying non-material stuff, information encoded in quantum entanglement, that has the same physical effect as some kind of exotic material pushing space-time apart? That's a massive claim.
It is, absolutely. And our mission here, for you listening, is to really synthesize the principles from quantum information science and modified gravity to see if we can actually prove this thesis.
Right.
We're going to focus specifically on how the structure, the components of this Qₘₙ tensor, how they generate this stability, and crucially, what testable signs we should be looking for if this theory is right.
All right, let's dive in. So let's frame that classical problem again, maybe dig a bit deeper. We've known for ages that general relativity, for all its power, isn't the whole story. Why exactly does it allow the math for a wormhole but forbid the physics?
It boils down to something called the null energy condition, or NEC.
The NEC. Explain that for us. Why is it the classical executioner for the wormhole idea?
Okay, so the NEC is a pretty fundamental constraint in classical gravity. Basically, it says that for any observer zipping along at the speed of light, the energy density they measure has to be positive, or zero. Think of it as saying, gravity fundamentally has to be attractive, or at least not repulsive. Anything with mass or energy that tries to violate the NEC and push things apart gravitationally, well, that's what we call exotic matter.
In a wormhole throat, that narrowest point, the geometry there inherently needs something pushing outwards to stop it from collapsing instantly.
Precisely. And wants to pinch off immediately due to gravity.
Yeah.
To keep that throat open, even for a fraction of a second, long enough for light to pass through, say, you need to exert this outward repulsive pressure. And that pressure requires negative energy density. It requires a big sustained violation of the NEC. Now, GR allows for tiny, fleeting violations like you see in the Casimir effect, maybe, but not the huge continuous violation needed to stabilize a macroscopic traversable wormhole. The classical physics toolbox it doesn't have the right tools. It's structurally insufficient.
Okay, so we need a theory where this repulsive effect isn't tacked on with imaginary matter, but is somehow built into the fabric of space-time itself. And that brings us to the Qμ framework. How does it change Einstein's field equations to allow for this repulsion?
Right. We keep the core geometric parts of Einstein's equation, the Gₘₙ and the standard matter and energy, the Tₘₙ, but we had a correction term, one derived purely from quantum information ideas. So the standard equation Qμ equals, constant times Tₘₙ, it gets modified. It becomes Gₘₙ plus lambda, Gₘₙ equals the constant times, bracket, Tₘₙ plus his new term, Qμ, which depends on entanglement.
Okay, Tₘₙ is the normal stuff, planets, light, radiation, all the things we know exert gravity. But now there's this entirely new tensor, Qμ. What does it fundamentally represent? Is it matter? Energy?
It represents the measurable stress energy contribution that comes directly from quantum entanglement and the inherent fluctuations in the vacuum. It's not classical matter, it's more like the energy structure derived from the informational content of the vacuum itself. And importantly, this structure isn't just pulled out of thin air. It's derived using thermodynamic principles applied to space-time geometry. It suggests this entanglement energy isn't just something we put in, it's something the geometry itself demands.
Let's pause on that synthesis point. If Qμ is just derived from entanglement, from information, why is it repulsive? Why does this particular kind of quantum stress energy provide the anti-gravity we need?
Okay, this is where we connect it directly to black hole physics.
Yeah.
It turns out when you apply this Qμ tensor to the inside of a collapsing massive star, the tensor naturally develops a huge repulsive component, and this repulsion is what prevents the singularity that general relativity predicts. GR says infinite density, Qμ says no. Instead of a singularity, you get a stable, tiny, Planck-scale object, a black hole remnant.
Ah, so the same force, the same Qμ effect that stops a black hole from crushing down to an infinitely dense point, that's the exact same force we need to stop the wormhole throat from pinching shut.
Exactly. It's a fundamental repulsion that kicks in these regions of extreme curvature, extreme gravitational stress.
So stabilizing the black hole remnant and stabilizing the wormhole throat, they're driven by the same underlying quantum fluid, this entanglement energy described by Qμ.
Precisely. Qμ provides the needed negative energy density locally, right at the throat, and violates the NEC there. But crucially, it does so without needing any hypothetical exotic particles. It uses only the known quantum fields and their entanglement properties.
That makes Qμ sound like an internal non-material scaffolding. Can we make that more intuitive? Is there an analogy?
Yeah, absolutely. Imagine space-time isn't just a simple rubber sheet. Imagine it's more like a super resilient, quantum entangled, maybe viscoelastic material. If you try to stretch it too far apart, compress it too tightly, which is essentially what the geometry of a wormhole throat or a black hole singularity tries to do, the internal quantum coherence, the entanglement structure within the material, resists that change. Qμ is that internal resistance. It's the tension or the pressure derived from the information content, the connectivity of the space itself. Yeah. You can't just arbitrarily squeeze or tear the vacuum because its own quantum entanglement pushes back physically.
The information itself generates mechanical stiffness. Wow. Okay, let's dig into how. How does the tensor actually generate that pressure? What are its components? Okay, saying Qμ is repulsive is one thing, but we need the mechanism. How does one quantum tensor provide all the different things needed for stability? Like the basic stiffness, the self-adjustment, the outward push.
Right. It's actually quite elegant. The Qμ tensor, apart from entanglement, it naturally splits into three main terms, or components, and each one plays a distinct, vital role in keeping that wormhole throat stable. They kind of work together to ensure the stability holds, regardless of the wormhole size or the immediate geometric stresses it's under.
All right, let's take them one by one. What's the first component, the one that handles the geometry's feedback?
Okay, that's the curvature energy coupling term. We often call the alpha term. Mathematically, it looks like alpha times Rₘ minus 1/2 Gμ Rs.
Rₘ is the Ricci curvature tensor related to how spacetime is curved. T is temperature. Why does curvature relate to heat, and how does that stabilize anything?
Yeah, the mechanism here is really profound. The T, the temperature, isn't ordinary heat like from a fire. It's the effective temperature that an accelerating observer would feel. That's the Unruh effect. And in regions of really high curvature, like a wormhole throat, the curvature itself acts like an incredibly strong acceleration field. So this alpha term directly links the local curvature to the local quantum energy state, this effective temperature.
So the intense geometry of the wormhole throat basically makes it act like a hot quantum system because of the curvature itself.
Exactly. And this constant alpha, it's enormous. It comes from black hole thermodynamics, and it's roughly 1.72 times 10 to the 67 Kelvin squared in standard units. I mean, the sheer size of that number tells you how strongly gravity and this quantum thermal energy are coupled at these extreme scales.
Okay, so if the throat is this region of immense curvature, how does this huge alpha term stop it from collapsing?
It creates a kind of self-regulating feedback loop. If the wormhole throat starts to contract, meaning the curvature, Rₘ, tries to increase even more, this alpha term immediately generates a proportional, incredibly dense quantum energy field. That energy density is directly tied to the curvature increase, and it pushes back instantly, stabilizing the throat. You can think of it like a geometric thermostat for spacetime itself. It prevents runaway collapse by converting geometric stress directly into repulsive quantum energy.
That's a powerful concept. Spacetime actively fighting its own extreme curvature. Okay, now what about the main repulsive part, the one that provides the outward push? You called it entropic gradient stress.
Yes, that's the second term, the entropic gradient stress term, or the beta term. It's written as beta times KB times.
Okay.
Essentially, terms involving the gradient of entanglement entropy, S. So, nabla mu S times nabla nu S minus a term involving the square of the gradient.
Okay, gradient of entanglement entropy, nabla mu S. For the listener, what does an entropy gradient mean physically, like a change in information?
Think of it like a pressure difference, but for information, for entanglement. An entropy gradient measures how quickly the amount of quantum entanglement, or coherence, changes as you move through space. If the entanglement is smooth and uniform across the vacuum, the gradient is zero, and this beta term doesn't do much. But if you try to violently rip apart two regions that are highly entangled, which is geometrically what happens when a wormhole throat tries to pinch off, that gradient becomes incredibly steep.
So the geometry is trying to break the informational link, and the information itself pushes back.
Exactly. This term mathematically treats that changing distribution of entanglement entropy as if it were a dynamic field. And that field generates enormous repulsive pressure. If the wormhole throat tries to contract, the entropy gradient skyrockets and the beta term kicks in, generating the massive outward pressure needed to keep that minimal surface, the throat, from pinching off. It's like the information flow trying to maintain its connection and exerting physical force to do so.
And this connects directly back to the black hole singularity thing we talked about. The fact that the remnant doesn't collapse must be this beta term in action.
It's the primary repulsive component, yes. The reason the remnant avoids a singularity is because the entropy gradient needed for that final collapse would essentially become infinite. And that triggers the beta term to generate an infinite outward pressure, stopping it. In the wormhole case, we don't need infinite pressure, just enough. We need a steep but finite gradient to maintain that stable open geometry. This term really embodies the idea that repulsive gravity is a thermodynamic necessity, driven by the need to preserve informational structure.
Incredible. Okay, one more piece. We need some kind of baseline structural integrity, something that provides stiffness regardless of the specific curvature or how the entropy is changing right now. What gives spacetime that fundamental backbone?
That comes from the third term, the quantum fluctuation stress term, or the gamma term. It looks like gamma times terms involving sigma mu, sigma nu, where sigma relates to quantum fluctuations. We can kind of think of this as the stiffness factor.
Okay, sigma terms derive from what exactly?
They basically arise from the constant unavoidable quantum jitters, the zero-point energy fluctuations that are inherent in the quantum vacuum. But the really critical insight here is the constant, gamma, its value, which is about 7.297 times 10 to the minus 3.
Yes.
It's not just some random number plugged in. Its value is fundamentally derived by linking this whole Qμ theory to the fine structure constant, alpha EM, from electromagnetism. And that link happens via the fractal dimension, dF.
Whoa. So you have a structural stiffness factor whose specific value connects gravity to electromagnetism through shared fundamental constants in this fractal geometry idea.
Exactly. It shows that Qμ isn't just some arbitrary fix we invented for wormholes. It appears to be a necessary piece of a deeper, more unified picture. The role of this gamma term, this stiffness factor, is to provide a constant baseline, scale-invariant contribution from the vacuum energy. It makes sure the stabilization mechanism works effectively across different scales. Whether you're talking about a tiny Planck-scale micro-wormhole or potentially a huge cosmological one, it's the intrinsic pressure of empty space itself.
Okay, if this Qμ theorem is really the missing piece, the key to quantum gravity,
Right.
then it shouldn't just allow stable wormholes. It feels like it should almost predict them, make them a necessary consequence of how reality is structured. Does the framework actually point that way?
It absolutely does. The constants we derive, the geometric structures like this fractal dimension,
Yeah.
they really only hang together mathematically if the vacuum has this built-in ability for self-stabilization and for forming these kinds of exotic, stable geometries. Let's look at that fractal dimension again.
All right, DFF, you mentioned it connects to the gamma term. Let's dig into that. What is this fractal dimension and how does it relate to stability?
Okay, so D, the fractal dimension, is defined as the logarithm of 8 divided by the logarithm of 3, which comes out to about 1.8928. This number isn't just pulled out of a hat. It arises from the mathematical structure of the theory, describing the effective dimension of spacetime way down at the Planck scale. It tells us spacetime isn't smooth and four-dimensional at its most fundamental level. It has this inherent microscopic fractal-like structure.
how can a purely geometric thing, a fractal dimension, be linked to fundamental particle physics constants, like the fine structure constant you mentioned? That seems like a huge leap.
Well, this is where the synthesis becomes really powerful. The mathematical framework shows that you need this specific fractal geometry, this df value, to correctly derive the known value of the fine structure constant, alpha EM. If spacetime had a different fractal dimension at the Planck scale than electromagnetism as we know it, it just wouldn't work the same way. The strength of the electromagnetic force is intrinsically tied to the deep geometric structure of spacetime through dm.
Okay, so the fractal nature is needed for electromagnetism. How does that same structure guarantee wormhole stability?
Because that same fractal geometry also dictates the properties of stable objects right at the Planck limit. We already saw it determines the size of the stable black hole remnant, right? About 0.726 Planck masses. It prevents the singularity. That specific geometry defined by df, the one that prevents the black hole's internal collapse. It provides the exact geometric template needed for a stable, traversable wormhole throat. The stability of the remnant and the traversability of the wormhole are, in a sense, mandated by the same underlying fractal nature of the vacuum.
That suggests an incredible unity. Okay, let's broaden the view a bit. This Qμ idea, defining geometry through entanglement. How does it fit with other big ideas in quantum gravity, like string theory or loop quantum gravity? Does it connect?
It seems to act as a kind of interpretive bridge. For instance, loop quantum gravity, or LQG, proposes that space-time is fundamentally built from these entangled networks called spin networks. Qμ provides a field-theoretic way to understand how those microscopic, non-local connections, the entanglement in the spin network, actually manifest as macroscopic geometric features like curvature. Basically, Qμ gives a concrete stress energy value to the entanglement links that LQG talks about. It makes those quantum connections physically relevant to the space-time metric we actually experience.
And maybe the most compelling conceptual link people talk about is the holographic principle, add SCFT correspondence, that kind of thing. If geometry really is information, then is a wormhole just the geometry showing a maximum information connection?
The connection there is direct and I think vital.
Yeah.
The holographic principle, especially through formulas like the Ryu-Takanagi formula, it established this profound link. The entanglement entropy between two regions is proportional to the area of a minimal surface connecting them in a corresponding gravitational theory.
A minimal surface, which, if you're connecting two different regions of space-time, that minimal surface is the wormhole throat.
Precisely. Now, in the Qμ framework, remember the beta term, it involves the gradient of entropy, nabla mu s. That gradient isn't just some abstract mathematical quantity in this theory. It is physically embodied in the space-time metric itself through that beta term. What this means is that geometric structures that link two highly entangled regions, namely wormholes, become the direct, inevitable consequence of space-time emerging from entanglement. Where entanglement between regions is maximized, the geometry itself must form a connection, a throat. So the Qμ theorem doesn't just stabilize wormholes, it argues they have to exist as the geometric expression of informational continuity.
Wow, okay. So we've gone from wormholes being this mathematical quirk needing impossible fairy dust to being a geometric necessity dictated by the quantum information structure of the vacuum itself. All right, the theory sounds elegant, mathematically consistent, but physics needs evidence. If Qμ is real, where do we look? We can't just, build a wormhole detector and wait. We need to test the stabilizing mechanism itself, presumably in the most extreme places we can actually observe.
Exactly. We can't build one yet, maybe ever. So we look where nature might build them, or at least use the same physics. We start with the most violent events we can currently measure. Gravitational wave mergers from black holes and neutron stars. We look for black hole remnant signatures.
Okay, black hole mergers. What specifically would we see in the gravitational waves coming off a merger that would tell us Qμ is at work, providing that stability?
So, standard general relativity, using the Kerr solution for a rotating black hole, predicts that after the merger, the final gravitational wave signal of the ring down should decay smoothly, exponentially, like a struck bell settling down. But the Qμ theory predicts the end state isn't a classical Kerr black hole with a singularity. It's this stable, fractal geometric remnant object with that dimension d around 1.8928.
And how does a fractal object ringing affect the gravitational waves we detect here on Earth, light years away?
Think about the difference between hitting a perfectly smooth bell versus hitting, say, a complex crystal lattice, something with internal structure. The smooth bell rings with a few clear, pure tones that die down predictably. The crystalline lattice, or our fractal remnant, would ring differently. It would likely produce additional, previously unconsidered ring-down modes, more complex, maybe higher frequency harmonics, almost like vibrations traveling through a solid like phonon modes. Finding these characteristic fractal modes in the gravitational wave data from mergers modes that are definitely not predicted by the standard Kerr black hole ring-down that would be strong evidence. It would confirm that the quantum vacuum, via Qμ, provides the necessary physical structure to stabilize these exotic geometries against total collapse.
That's a direct test of the stabilization mechanism. Very cool. Okay, what about bringing it down from astrophysics to the lab? Can we test this link between entanglement and gravity here on Earth?
Potentially, yes. This leads to the idea of quantum interferometry phase shift experiments. The Qμ framework predicts a very subtle but potentially measurable effect when you put a single massive particle into a quantum superposition. It specifically tests the impact of that alpha term we discussed.
Okay, so you take a particle, split its quantum wave function so it travels along two different paths simultaneously, and then bring the paths back together to interfere. What's the predicted anomaly? What should we see?
The theory predicts that the total phase shift, the difference in the wiggles of the wave function between the two paths, delta phi won't just be the standard quantum mechanical shift plus the normal gravitational shift. There should be an additional term. And this extra bit of phase shift depends on the particle's mass, that huge entanglement constant, alpha, and crucially, the difference in entanglement entropy, delta S, the particle experiences along the two different paths. The prediction looks something like delta phi total equals the standard delta phi qm plus a factor times gm squared over h bar c times alpha times delta S.
Okay, so the extra gravitational effect is explicitly tied to the change in quantum information, the delta S between the paths. You're essentially trying to measure the physical push or pull of the quantum vacuum's entanglement structure on a superposition.
That's a good way to put it. It's the ultimate benchtop test for the alpha term's existence and its predicted magnitude. If experiments can isolate this tiny additional phase shift, it would be huge. It would validate the core principle that quantum information, entanglement entropy, dynamically modifies the local space-time geometry, proving that entanglement directly influences the metric in a controlled lab setting. That's the fundamental step needed to believe Qμ could actually hold a macroscopic wormhole throat open. It proves the link between information and force.
All right, astrophysical tests, lab tests. But if Qμ is a fundamental change to gravity, it has to work everywhere. At the biggest scales too, the cosmological scale. Can the same physics that stabilizes a tiny wormhole throat also solve the two biggest puzzles in cosmology right now? Dark matter and the Hubble tension. That seems like a tall order.
It is a tall order, but this is perhaps the most compelling claim of the Qμ theorem, the idea of scale-dependent coupling. The argument is that the same underlying physics, the same parameters within Qμ that stabilize a wormhole, when implemented correctly in cosmological models, must provide a coherent explanation for everything from galaxy rotation to the universe's expansion. It's usually formulated through a scale-dependent coupling function, let's call it alpha k, where k is wave number and z is redshift.
Okay, how does the repulsive aspect of Qμ get rid of the need for dark matter?
Primarily through that beta term, the entropic gradient stress. On the scale of galaxies, the argument goes, the entanglement structure of the vacuum itself modifies the effective gravitational field. So the observed rotation curves, the fact that stars way out in galaxies orbit much faster than they should based on visible matter, aren't explained by adding loads of invisible dark matter. Instead, they're explained by the inherent modification of the gravitational potential itself, caused by Qμ. The extra gravity needed comes from the entanglement pressure, not from unseen matter.
Okay, so it modifies gravity on galactic scales. What about the expansion of the universe? The Hubble tension, the disagreement between measurements of how fast the universe is expanding today versus predictions based on the early universe.
The same fundamental repulsion from Qμ, particularly when considered over vast cosmic distances, acts effectively like a negative pressure. It contributes to the accelerated expansion, similar in effect to what we currently call dark energy. By calculating the universe's entire expansion history using the modified field equations that include Qμ, the framework predicts a specific value for the current expansion rate, the Hubble constant, h0. The predicted value comes out around 68.2 kilometers per second per megaparsec, and that value lines up very well with the late-time measurements from supernovae and other local probes, potentially resolving the tension with the early-time measurements from the cosmic microwave background.
That is quite a synthesis. The same quantum entanglement effect that stops a black hole singularity, opens a wormhole throat, also dictates how galaxies rotate and how fast the entire universe expands.
If it holds true, yes. Finding coherent fit across all these scales, from the tiniest Planck-scale remnants, to lab experiments, to galaxy dynamics, to the whole cosmos, that would be the ultimate confirmation. It would strongly suggest that the underlying quantum geometric reality described by Qμ is the missing piece in our understanding of gravity. And in that picture, stable wormholes aren't just possible. They become an almost inevitable consequence of a universe whose geometry is fundamentally woven from information. #outro. So, to just sort of wrap up what we've explored here, the Qμ theorem really offers a profound shift. It suggests we don't need to invent non-existent exotic matter to stabilize wormholes. Instead, the stability comes naturally from the entanglement stress-energy tensor, Qμ, which is already part of the quantum vacuum. Its components, that curvature feedback, the entropic pressure, the baseline stiffness, they work together to make stable, traversable wormholes, a natural, maybe even necessary, feature of a universe governed by quantum information.
And the implication for you, the listener, is pretty mind-bending. We might need to start thinking about gravity and space-time structures, black holes, galaxies, maybe wormholes, not just as matter-bending space, but as the physical shapes, the geometric expressions of an underlying network of quantum information, of entanglement. The universe as a vast entanglement network, and things like wormholes are just the most direct paths, the geometric shortcuts through that network.
Which leads to a final, pretty provocative thought. If the stability of that wormhole throat is mathematically driven by these gradients of entanglement entropy, by nabla mu s, what happens when you actually use the wormhole? Does the very act of sending information through it, which inherently changes the entanglement entropy between the entrance and exit, it changes that gradient? Could that fundamentally alter the wormhole's own geometric stability? Could traversing it depend somehow on the amount, or maybe even the type of information you're trying to send?
Now that is something to chew on, a true deep dive for another time.